to welcome today's session speaker, Dr. Santosh Kumar Vipparthi, who is going to talk us about moving object detection in video. Dr. Santosh Kumar Vipparthi, a senior member of Triple IT, I am Triple IT. He has 11 plus years of experience, including teaching and leadership. Currently, he is an assistant professor in Mehta Family School of Data Science and Artificial Intelligence, Indian Institute of uh, Guwahati. Before this, he served as an assistant professor in Department of Computer Science and Engineering in Malviya International Institute of Technology, Jaipur, a national importance, one of the top NIT fully funded by Ministry of Education, Government of India. He received PhD MTech degree in system engineering from IIT Varanasi in 2014 and 10 respectively. BE degree in Electrical and Electronics Engineering from Andhra University, Andhra Pradesh, India in 2007. Dr. Vipparthi research in an area of computer vision, deep learning, ATC. He successfully supervised 3 research scholars and is currently guiding 7 research scholars. The area of interest of Sir, deep learning, image retrieval, expression recognition, aerial image analysis, face recognition, and motion detection. Thank you, ma'am.
Thank you, Kundan. Dr. Santosh Vipparthi is a very dear friend of mine, and from past somewhere around 7 to 8 years, we have known each other. And it's really nice. He has recently joined IIT Guwahati. He has a vivid experience, and it would be a very, very beneficial and great listening to him. Thank you so much, Dr. Santosh, for accepting my invitation and accepting to come here for this workshop. Thank you so much.
Yeah, first of all, I thank coordinator Dr. Pooja for inviting me to this wonderful sessions. So Triple IT Nagpur. So congratulations to you people also.
Thank you.
Yeah, thank you. So okay.
Over to you, sir. Yeah, it's visible.
Yeah, thank you. Today we're going to discuss about some research challenges and what are the problems, how we can able to address the problems and all in the field of change detection or moving object detection. We'll go to discuss. If anybody having any doubts in between, please feel free to chat here or unmute yourself and you can raise the questions. I hope my things are visible to you, right? So as myself is Dr. Santosh, working at working at IIT Guwahati. So the main intention of this particular aim of this particular application is moving object detection is, as you are able to see, moving object detection is nothing but you are trying to detecting the moving objects in a given video. So why only video? Because in a static, in a single frame, we may not able to get the moving things. So we need to find those changes which are happening in a given frame sequences or in a given video. Now the question comes here is, why should we do? Because this particular application of change detection, the problem of change detection can be applied in many of the computer vision problems as a fundamental task. Why so? We're going to discuss those things slowly. So you try to understand this is actually the part of change detection or moving object detection or foreground segmentation concepts. So here the objects, here we are talking about only the objects which are moving can be detected with the binary segmentation strategies. This is a basic conventional way of solving a particular problem called change detection. So as we have, as I already mentioned, that this is a multiple different ways of solving a problem of a change detection. The rightmost side, whatever you are observing here, the original frames and the corresponding ground truth information is this. So if you try to observe the rightmost side, here the entire background is in black color and the rest of the information which are in a white color, right? So this is called foreground segmentation. Now the question comes here is, this is what our actual aim is. But the question comes here is how to train such type of, how to get such type of an output from a given video sequence is our target. Now, do we have any other alternative way to give a similar solution on this in this particular application? So the answer is yes, we can solve the similar problem of foreground detection or a moving object detection with the help of bounding boxes. So this is called axis aligned bounding boxes. This problem can be also called as MOR, moving object recognition. Now the further question comes here is, here whatever you are things you are seeing on the rightmost side, this is a simple conventional way of solving a problem. That means here the video sequences which are available in a normal view. But can we apply the same thing from the aerial view? Yes, of course we can do we can solve the problem from the aerial view. We will try to discuss some of the problems in the aerial and conventional view together. So what are the basic approaches generally we generally follow to get the solution is, these are the three basic steps. First one is, in a given video sequence, first you try to estimate the background. So background is nothing but here the things which are not at all moving. If any of the object is not moving for a particular time period, that will be comes under background information. So if you try to observe in this particular frame sequences here, there is a snowfall and there is a background trees and there is a car behind, and there are few people who are trying to walk here in this frame sequence. So in this given input sequence of k number of frames, first we need to estimate the background. So let's assume once we have estimated a background, then what we need to do it. The next step is that we need to estimate the saliency map. So what is meant by saliency map? Saliency map is nothing but once you have estimated a background, then you try to find out, is there any change of information is there in my current frame. So the current frame which I have said right now is nothing but at a time called t, you are trying at a time called tth frame, you would like to estimate whether is there any changes are there or not. So what about the previous frames? With the help of the previous frames, you are trying to estimating the background. Now at a time called t, in between the estimated background and current frame, you are trying to take the analyzing between the two frames, that is called estimated background information as well as the current frame information. There you are trying to estimating, is there any salience information is there or not. That means is any motion information is there or not. That is the second step of for calculating the saliency estimation. Once the motion estimation is done, then we are foreground segmentation. So these are the three different steps generally we used to follow to get the desired output. So what are the applications where we can use these particular change? So the application of change detection can also be used in this particular intrusion detection problems, can also be used in the traffic monitoring. And in the traffic monitoring, if you'll observe here in the traffic monitoring, the number of vehicles we can count, and also you try to observe this particular image here. These are the two vehicles which are trying to cross the lane without any proper indication. That means they are trying to violating the rules, right? So in the traffic monitoring, if required, we can also further do the high level processing for anomaly detection or driver behavior analysis. That also we can do it. Now this is another interesting problem here is violence detection, whatever you are able to see it here. Now here in this particular image, you try to observe this particular image is an anomaly detection part. Why we have declared this is anomaly detection? Because there is a person who wear a mask and holding a gun, and he is trying to aiming this gun towards the shopkeeper, right? So there is some set of operations are executing, or some of the operations are happening in a given sequence, because the person is trying to holding a gun, so the gun is comes under violent device. So the person is also trying to aiming, that means the posture of a person is towards the shopkeeper. So this particular activity can be considered as a violent activity. So in order to do the violent detection, we can go for this particular object detection concepts and posture concepts, and so action recognition. By integrating these three, we can conclude a thing. But now you see the thing. This here is a person who is trying to aiming a gun, because, and we are calling it as a violence activity. But the reason here is the person is entering into a normal shop. But you take the same action in a shop where the person has entered to and entered in a gun shop itself. The shop itself is having these particular guns and all. Now let's assume this particular action. Can you conclude this is a violence activity? We may not able to conclude that is a violence activity, maybe because he might be trying to testing a gun. So in such situation, the same action, the same posture now comes under normal activity. So what was the reason here? Is not only the action and object detection is playing the role, also a background information is also trying to play a role. In this particular sequence, the background information, background is something like a normal shop. But whenever this violent activity will become a normal activity, whenever the person is trying to entering into a gun shop. So this is the basic challenges. So we need to also we need to analyze the background information. Now coming to the further analysis, that anomaly detection here. So we can use this particular concept for anomaly detection also. So now here we need to define the first anomaly. Then based on the anomaly, we can able to develop an algorithm. Now detection based tracking. Now most of the few startups in India, they're trying to focusing on analyzing the sports, or they're trying to developing a system which is going to it will going to give a recommendation to the trainers. So much of the research is also going on in this direction. And crowd monitoring. Crowd monitoring is one of the interesting problem in recent times, especially in COVID situations. So in a particular mall or in a particular place, if the crowd is going to be gathered, then we can able to monitor it. Now, in this particular monitoring of a crowd, again the background information is going to play a role. Let's assume in a mall, supermarket, in a particular shopping center, in a mall, the crowd is gathered to watch a particular concert. There is a musical event, some concert is going on. Now there the crowd will going to be gathered for sure. So crowd gathering in that particular same mall to attend a concert is a normal activity. But let's assume there was a small accident in the mall. Crowd can also gather. In such situation, the crowd gathering can be used to estimate the anomalies. So now, depending upon the background scenario and further some situations, we can able to take the conclusion on a particular application. I mean, we can integrate these particular problems together to get a final solution. Now the another interesting problem is in this change detection from the aerial view. Till now, whatever we have discussed is a normal conventional views, but now we can also use this particular concepts in the aerial view, because the availability of the drones are very cheaper in nature. So we can afford the UAVs or compact UAVs. So research in that particular field is also going to be increased. Now you try to observe here the UAV. With the help of UAV aerial views, we can try to observe the remotely monitoring the particular areas, especially in the disaster responses. We can able to use it, and right, these are things we can also do it from the aerial views. Now, what are the basic challenges generally we're going to face whenever you're trying to apply any of the change detection algorithms? So these are the few challenges. First one is the camera jitter problem. This is one of the fundamental problem which we need to solve before detecting the foreground information. So what was that fundamental problem? Let's try to see here. At a teeth frame, this is the frame information. This is a T+1 frame. That means the data acquisition device itself is disturbed or shake because of any external problems, maybe weather conditions or anything. So that the time it is going to acquiring the data, if the object is the camera itself is shaking, then there is a small difference in the video frame. So if you try to observe these particular two frames at a teeth frame and T+1 frame, now the green part is almost like a similar part, but if you try to observe in the red bounding box, where you can able to see in the left side and right side there is a difference. So this is a very quite common problem, because if you try to take the pixel wise differences between these two frames at this particular location, you will going to get a difference. Definitely you will going to get there is a difference, but the difference is happened just because of the camera jitter problem. It is not because of the actual movement of the vehicle. Now, dynamic background. This is one of the interesting problem which generally going to occur, which we need to solve actually. The dynamic background is nothing but where your foreground information, let's assume the case where you're standing in front of one fountain or in front of, you're in one side of the lake, and the region of interest, the vehicles you are trying to monitoring is in other side of the lake, but in between there is a fountain, let's assume. Now, as per the properties of the fountain, the functionality of the fountain will going to be vary from time to time, right? So whenever you're trying to capturing any of the video, as the fountain is under functional, as time goes on, the and in between the frames you can also able to see there are the changes, but these are all the changes just happening because of the functionality of the fountain, or because of the wind, the leaves movement can be, there is a movement in the leaves, but this is an actual natural scenario. It is not an actual true motion of any of the object. But as such type of as such type of changes will be appear in a frame, we need to detect that and we need to surpass that. We need to detect that particular changes and we need to conclude these changes are belongs to the background, not to the foreground. So this particular thing also this type of challenges can be comes under dynamic background. And illumination changes, this is one of the biggest challenging problem. As time goes on, the changes at different locations will, as time goes on, the lighting conditions can change, vary. So whenever you're trying to take the frame difference between the two frames at a longer duration of time, then definitely you're going to get the change between the frames. It may going to happen because of the lighting conditions. If you observe in this particular diagram, at a T frame we have n number of lights, but at a T plus 10th frame there are some changes, and T plus 20 frame there are changes. So as the light is also played an important role in the pixel intensity values, so that when difference between the pixels may go into, there may be a difference between the pixels because of the lighting condition. That also we need to consider. And camouflage is another problem where your background information and your region of interest, the foreground information having a similar color. So here the person is wearing a red color jacket and background is also red color door. And here you try to observe, here there is a in the airport, the color of the background and color of the flight is in similar color. So you try to observe in the green bounding box, there is a flight which is actually coming. So there is a vehicle, but if you see the background and foreground information, the observing this particular vehicle is another challenging problem. This problem is called camouflage. And challenging in weather conditions is very quite common, especially in North India. You can able to see there is much challenges, and fog information will be there during the winters. So detecting the objects in the foggy environment is one of the biggest challenging problem. And shadow is again a quite common problem in video sequences. So as you move on, the shadow will also follows you. So there is an illusion which is going to be created in a video, created that the shadow can behave like a one independent object. Now we need to develop an algorithm in such a way that the shadow information has to be surpasses, only the true motion information needs to be detected. So these are the few challenges which are generally we're going to see in the change direction or foreground segmentation problems. There are a few more. Now coming to the problem from the aerial view perspective. So if you want to solve the problem from the aerial perspective, these are the few additional problems or few new problems we can able to, or few challenges we may need to address. The first one is number of objects in a given single frame. If it is a conventional view, the number of objects will be very minimal. So finite number of objects will be there in a single frame. But whereas in the aerial view, the same problem may not going to, the similar problem may going to be validated, because here in a single frame you can able to see n number of objects. So the dense objects are going to be a problem. And another important thing is that the size of the object from the aerial view. So here the size of the object is very smaller in size. So now we need to develop an algorithm for the tiny object. So this is like a tiny object detection and tiny object tracking, and detecting a tiny moving object detection. Now from an aerial view, the shape and structure of the object will going to change. That is a problem. And at the in In addition, we have a problem of these particular occlusions here. You try to observe here, there is an occlusion. Yeah, if you'll observe here, there is an occlusion. Already the size of the object is very smaller in size, but it creates an occlusion is also another problem. So still we need to handle that. Now here you see, this is the two white color cars and this is the two black color cars. The black color car, which is going to create an illusion of there is a small patch in the on the roads. So whenever the roads are going to be damaged from the aerial view, such type of holes we may can able to observe, right? So this particular car is creating an illusion of that hole on a road. So we need to detect that particular parts also. Now in the traditional approaches, what are the general? I think there is a small disturbance in this particular slides. I don't know why. We'll correct later. Yeah. In the traditional approaches, what are the general procedure researchers used to follow? In the traditional approach, let's assume this is some video sequences. Here's a video. This is a set of frames sequences. From a given frame sequence, first we need to extract the features. So in order to extract the features, either you can take the color, edge, spatial features, or temporal features, or anything. So there are different set of feature extraction strategies are already adopted in the literature. These are all handcrafted or traditional techniques in the literature to solve the change detection. Once you have extracted the features, then we need to go for the background modeling. So in the background modeling, there are two important steps which are involved. The first one is background initialization. First, we need to initialize the background. As I said that, let's assume you have 1,000 frames are there with you. From 1,000 frames in a given video sequence, first you can take initial 10 frames. So first you initialize the background frames. So initial 10 frames are there. Now you first estimate the background out of 10. So by taking the help of 10 frames, we have estimated one single frame that is called background frame. That is called background initialization. Now as time goes on, you need to maintain the background. Is nothing but initially 10 frames you have considered for the background estimation. Now 11th frame you are going to analyzing with reference to the estimated background. If you found any changes in the 11th frame, then there may be a foreground information. But if you found there is no changes, I mean 11th frame is almost equal to the 10th frame, almost equal to the estimated background, it means that 11th frame there is no motion is involved. So you need to update frame. That is called you need to maintain the background. So 11th frame will go to the background frame. Similarly, we need to maintain. So initially we need to initialize the background. Later we need to maintain the background as time goes on. So which frame is having a foreground, you can skip that frame, and wherever you find out that there is no motion information is there in a particular frame, you can update that into the background frame. So once you have done the background, then we can go for the foreground detection. So these are the few techniques which are there in the literature, the color, edge, spatial, and so on. Similarly, background modeling can also be done with the different strategies like parametric, non-parametric clustering, and so on. Foreground detection is the classification or thresholding concepts. So if anybody interested to see this particular literature survey in the traditional approaches, so this is one of the good article which is published in Transaction of Image Processing. There the others have clearly explained the strategies here. So in the literature, in the non-deep learning techniques, the problem have solved in this way. The features can be extracted either with the pixel level methods. Pixel level means each and every pixel in a given video, a given frame is going to be considered for calculation of foreground and background. So most widely implemented and process each pixel independently. Region level is nothing but, as you know, the mask processing. Grid, mask, right? Like in a convolution operation, we are going to take the 3x filter size, right? Region is nothing but, instead of trying to taking a single pixel, you are trying to take the interpixel relations. That means a group of pixels, size 3x3 or size 5x5 or size n×n, depends upon your requirement. So there you are trying to take a decision whether the given pixel with the neighborhood is having foreground or not. And there are few more algorithms in the literature if you'll observe. They might be use the hybrid methods. That means they are going to integrating both the pixel level as well as the grid level, or as well as the neighborhood relation also they might be taken. That is called interrelation, interpixel relations also combined together. Now interactive mode model completion, interactive mode completion, and missing data reconstruction. So what are the method you are going to develop for? What was your ultimate aim? If your aim is to your model supposed to work on the real time, then the algorithms are different. If your model wants to use it for the post processing, then strategies could be different. So based on this different approaches that others have followed in this particular literature article, the information is clearly available. Now coming to the deep learning approaches. There is a small difference is there in the traditional approaches and deep learning approaches. Reason is, in the traditional approaches, the entire procedure has followed on a unsupervised learning strategy. You don't require any of the ground truths, or you don't require any of the learning concepts in the conventional problems of change detection. But whereas in the deep learning, the situation is a bit different, because you need to train your model with the help of the labels. So here in the deep learning, people have used the supervisor techniques. So while they're following the supervisor techniques, there are some technical differences are there that we're going to slowly address. So in the, if you further analyzing in the deep learning, this is a few literature you can consider. There are few articles which are differ by the way they are going to feeding the inputs to the deep learning model. Few people have feeded only single frame. Few people have feeded a sequence of frames or some subset of frames and so on. So the number of frames you are trying to feed to the model will definitely going to play an impact on the result. Now, once the input frames have fed to the encoder decoder networks, so within the encoder decoder, these are all the few different type of techniques you can able to observe in the literature. Few might be used CNN models, few might be used 2D CNN, 3D CNN, few might be used auto encoder decoder, GANs and LSTMs and combinations and so on. There are, you can able to get n number of articles with the various combinations. So these are the publicly available data sets in the field of change detection. These are the few popular and publicly available data sets. So if you'll observe here the CDNet 2014, this is one of the popular data set which is widely used in the field of change detection. And this is popular because of the number of challenges that is available in this particular data set. But yes, these particular few data sets are popular in the non-deep learning techniques. Now people are also using the deep learning techniques. So if you'll observe here, these are the few data sets, like some few natural data sets, few underwater data sets, few thermal data sets are there already. These are freely publicly available. If anybody interested, they can use on this. So few evaluation matrices here, precision recall and F1 score and so on. And if you want to go for the bounding box, there the procedures are a bit different, because in the bounding box we need to go for the IOU. Now let's discuss about a very brief on this traditional approach, so that you may going to understand the other differences in the deep learning. So in the traditional approach, this is one article, if you'll observe, is a candid approach. The entire approach is aiming to solve one particular problem. Let me give you the direct answer for that. Yeah, the main aim of this particular candid is to handle the dynamic background information. That means wherever I have this particular fountain information is there, so fountain is also creating an illusion of a motion, right? But this is not the actual true motion in a given data. Now you try to observe this diagram here. There is a vehicle which is going on backside, right? The way there is a car which is going in other side of the lake, right? So this is that particular car only we need to detect, but the information which are there in a given frame, there is a fountain also. So you try to observe here the ground truth. The ground truth, there is no fountain information. Only that particular the movement of the car is only available. So we need to develop an algorithm in such a way that it has to detect only that particular car information. So this particular candidate operation is trying to solve this particular problem dynamic background. This particular algorithm is only meant to dynamic background. Now you try to observe here. This is a vehicle which is going to detect it. So the model has tested on CNET 2014 datasets. These are the few results, qualitative results. Now this is another non deep learning approach. This particular entire concept was used with the help of neighborhood operations or descriptors you can consider. This is a descriptor. So this is one descriptor, antithetic isometric cluster pattern concept. So the aim of this descriptor is to find out the now you try to observe here. The aim of the descriptor is to find out the lines and curves and corner points in a given input data, where other popular techniques of descriptors are failed. But this is not the actual purpose of this particular antic. So this paper is trying to address two different problems. One is retrieval, another one is change detection. If you want to go for the change detection, there we have introduced a concept called inter and intra. The main idea of this particular antic is to solve the problem of shadow. So as we have already discussed that shadow is one of the biggest problem, right? So if you'll see this particular shadow information here, so from a given sequence, first we can estimate the background. So let's assume this is the background information which you can able to see it here. So from a background information, we can calculate the inter and intra descriptor. That is called antic features. So from inter you will get 8, and from intra you will get the 8. So combining this, you will get 16 features at the particular location. Now let's assume whenever you are trying to find out a shadow region where you are able to see it here. Yeah. This is a shadow region. So at the shadow region, these are all the pixel information. Now you try to take the Hamming distance between the estimated background and the information which you have currently estimated at a particular Tth frame. Let's assume wherever you're trying to analyzing the instead of shadow actual foreground, that means wherever the person is trying to actually move at the leg portion, you try to observe here, which we have highlighted. There, these are all the features depending upon the properties of the antic descriptor. Now again, you try to take the Hamming distance between the features here and estimated background. Now, if you see the Hamming distance for the foreground is 8, and wherever the Hamming distance for the background is 2. So in this paper, we have considered the 50% of the Hamming distance. Wherever the Hamming distance is greater than 50%, equal to greater than equal to 50%, it can be considered as a foreground. Otherwise, it can be considered as background. So that is how the shadow information can be surpassed. So how these particular features will come? This is the actual strategy of this particular descriptor. This is called handcrafted descriptor, you can consider. So the model have already tested on various data sets, and if anybody interested, they can go for it. Now coming to the deep learning approaches. So whenever you are going to see in the recent terms of deep learning, it is because it gets a lot of attention, right? So deep learning concepts also used in most of the business analytics problems also, but there is a small problem which was observed, that inconsistent training and testing data division strategies. So this particular inconsistent testing and training data division strategies, which will going to impact very badly on the performance of the model. That is the first observation. The second observation is, whenever a person has used this inconsistent data divisions, how we can able to compare our models with them? So that is another problem. So if you observe the much literature, there are a lot of problems in the data handling issues, because the deep learning strategy is a supervisor concepts in the field of change detection, where training concept is introduced, but whereas in the non-deep learning techniques, this training concept is not there. So there is no such type of data divisions and all. Each and every frame comes under testing data only. So take a data, and each and every frame you try to analyze, estimate the background, maintain the background, find out the foreground. But in the deep learning, the things are different. So that is where this particular technical differences came into the picture. Therefore, there is an article where these particular actual issues are specifically addressed. So in order to address the problem, in order to solve this particular problem, so in literature, there is an article there they have introduced this particular problem of scene dependent evaluation and scene independent evaluation. So data evaluation is one of the major important part to get the generalization capability of the model. So what is meant by scene dependent, scene independent? Scene dependent is nothing but, let's take this example, visual slide, you will get to know. You try to observe this particular scene dependent evaluation. Let's assume you have one category. Let's assume you have a category where the category is having 4 set of videos, independent videos. Now, as it is even though it is an independent video, you need to divide this particular data into 2 parts. One is a training set, another one is a testing set. Now, if you try to observe this particular training data and testing data, could you able to correlate anything between these two? Do we find out any similarity between these two? So if you see the similarity between these two, the background information used in the training and the background information you would like to use for the testing is remains same. Almost every information is remains same because the n number of frames are simply divided into some ratio, maybe 50-50 or 80-30 and so on. So as you have trained your model with such type of a background and you're trying to test your model with the similar type of background, then the accuracy will be definitely will be higher. But that is not the actual case we're supposed to follow. So there is a scene independent evaluation is also there. So what is meant by scene independent evaluation? This is a strict scene independent evaluation is nothing but, let's assume a category is having 4 set of videos. You try to use 3 set of videos for the training, but you try to test the data with the completely unseen video. That is, so as you can see it here, because the training data information is completely different as the with respect to the testing data, because background is different and things also different except the cars. So here in this case the background is going to play a very important role. So this type of data division is called scene independent data division strategy. So coming to the okay, any questions as such? If you have any questions, please
Put in your questions either on the chat box or you can unmute the mic. You can continue, sir.
Okay. So this is one article to solve the problem of moving object detection in 2018, one article. And the limitations of the article we're going to discuss. This is one of the basic article during that time, the field of change detection. So there is some set of frames, initially some k number of frames. In this example they have used 100 frames in this paper. From this 100 frames, first step is we need to estimate the background. So they have used the temporal median is an background estimator. So they adopted this particular temporal median, that is called handcrafted approach to estimate the background. Okay, once you have estimated a background, what is the second step? So they have used this particular estimated background to find out the forward information. So what they have passed this particular current frames as well as the estimated background, and with the help of the estimated background they have taken the saliency map from the each and every current frame. Then they pass to encoder decoder to find out the forward information. This is one of the simplest network they have followed. But what type of the problem they have observed here is, try to see this. Yeah, so this is encoder decoder basic thing. The basic problem here they have addressed here is, one thing is traditional approach they adopted, fine. Second thing is the way they divided the data. So the n number of frames, that is called 18,000 frames, whatever frames are there, that frames are divided into training data and testing data. So 12,000 frames something used for the training and remaining used for the testing. Now the question comes here is, what are those 12,000 frames? From where this particular 12,000 frames came to the picture? So that information generally not available. So they may, so the others can initially might be selected or what are the strategy they might be followed. So this is one article, and another article from the same group. As per the article details, this is the first article in the field of change detection where they have provided a complete end-to-end solution using deep learning concepts. How they have done a complete end-to-end deep learning solution? You try to analyze this particular network. So in this particular network, they have introduced three different modules. One is a BENet, SMNet, and FZNet. So BENet is nothing but background estimated network. SM is nothing but saliency motion network. FZNet is nothing foreground network. Now, what is meant by BENet? What is the aim of the BENet? So here the aim of the BENet is to estimate a background. How they have estimated? So initially they have used the 50 frames. So what they have done, the entire data set is divided into chunk of 50 frames, 50, 50, 50, 50, 50. So initially they fed 50 frames. From at 50 frame, they have used a temporal pooling, so they got 1 frame. Then they have applied few convolution operations. Then they generated one background frame. Now they have replicated this background frame to 50 number of times. So the replication, aim of the replication is to calculate this particular differential layer, because they want to estimate the changes of each and every frame with respect to the background, estimated background. So they replicated this estimated background 50 number of times. Then they concatenated with the original input data. Then they have applied the differential layer. So 50 frames now become 100 frames after concatenating with the replicated layer. So they got these differential layers. Then they gone for the max pooling, then encoder decoder concept. This is so simple. So this particular algorithm was implemented in the MATLAB. That is the reason they have used this replicated layer, because as it is in 2018, there is no such articles are available. So they might be implemented in the MATLAB, that as per that particular paper article. But here the question comes here is 50 frames as a chunk they have created. Then they divided this training data and testing data. So similarly, the scene dependent evaluation, scene dependent scenario is also appear in this particular article. That is another problem. Even though there is a complete end-to-end solution, the results definitely will going to be boosted because of the scene dependent evaluation. And this model has tested on many data sets as well. If you're even interested in, you can just go through this. Now, in order to overcome these particular issues, there is an article that is called scene independency method, because is that background really important? An empirical study of scene dependent and scene independent evaluation for CNN based change detection. So this article was proposed to address the issues of this particular data division strategies. So how much these particular data division strategies are going to play an important role, we'll discuss in terms of the performances. Okay. Now you try to observe this particular diagram. So here the data division itself is not an important aspect. Also, the network is also an important part. So if you'll see in the literature, the articles as the data is in a scene dependent evaluation form, performance will be definitely higher. So now in order to prove that scene dependencies played a role, so we also need to develop an algorithm. So this algorithm is aimed to do the change detection with the help of few blocks. The first block here is the DRBE block. So what is meant by DRBE block? Here the DRBE block is depth reductionistic background estimator. So for this, initially they have considered the initial 50 frames as a temporal sequence. From this particular 50 frames, first they have passed this particular initial frames to MMSR block. So what is the aim of the MMSR block? Here, if you try to observe the MMSR block, it is consisting of multi-scale features. So first one is 1x1 convolution, 3x3 convolution, and 5x1. If you look at the properties of the MMSR block, even though it is a 1x1, 3x, and 5x5, from out of these three, they have extracted a maximum pixel at that particular location. So the max of 3 is going to be taken to form a particular frame. Now this operation is further repeated twice If you're interested, you can stack 2 more times, or you can reduce to 1 time, and so that is all up to you. So in this particular article, they have done the stacking of twice by gradually reducing the depth of the frames, because initially the time series is 50, but you need a single frame, so that means 50 frames to 1 frame we need to convert. This is what they have mentioned about the DRBA. Now coming to this particular current frame. So from a current frame, we need to estimate the saliency map information. So the estimated background and current frame by passing to same MSR block to get the forward information, concatenate all together and pass it to the encoder decoder network. So this is a pictorial representation of this particular DRBE block with the help of MMSR. Now initially I said it is a 50 frame, initial 50 frames are there. You pass it to the first MMSR block. You try to observe initially it will going to be estimating some of the forward information. Later on the second and third, we are trying to polishing that particular information so that only background can be left out. So by repeating 3 times of MMSR, at the end we got this particular background information. Now MMSR is a multi-scale feature, so definitely it will go to extract the features. So from a current frame, you can pass it to the MMSR, you got some features, and you concatenate all the things together and pass it to the encoder decoder network. So as I said, if you observe this particular table, except this particular non-deep learning approaches, like as I have seen here in the lean is a non-deep learning techniques, and rest of things are the deep learning techniques. You try to observe rest of the deep learning techniques, they all have used the scene dependent evaluation strategy, but only non-dependent techniques will going to follow the scene independent evaluation. So in this article, if you'll observe here, you can able to see the results of both in scene dependent, also in the scene independent. In both the results are, you can able to easily see it here. So question comes here is how to divide the data. There should be some strategy so that anybody can able to follow, right? So the strategy here is, let's assume you have n number of categories. There you can able to follow this particular leave one video out strategy in scene independent evaluation. Let's assume you have each category is having 4 videos. You take one video separate and you can use the rest of the videos for the training. So which video you have used for the training and which videos you have used for the testing, the things are very clear. So the experimentations in this algorithm has already done in 2 different ways. One is if your data set is having 10 categories, for example, each category is having 4 videos. That means you might be having a 40 videos, right? From each category, you can take one video as a testing. So how many videos we left out? Total 30. So if you try to train your model on each and every category, that is called category-based training. But if you wish to train on complete data, that is called complete data. That means you can combine all 30 set of videos together and train your model, and you try to test with the remaining 10 set of videos. That is separately for the testing. That is called complete data training in the scene independent evaluation strategies. Now, to prove the difference between the independent and dependent, also dependent evaluation also done. Here the data driven strategies are so simple and clear cut. There is no frame selection, there is no trimming, there is nothing. Suppose let's assume you have n number of video, the video size may be 1000 for example. Simply this divide the n number frame to n by 2. So you can use initial n by 2 for the training, and you can test with the rest of the n by 2 for the testing, or vice versa. Anything can be fine. So in this particular things, the way the scene dependent evaluation is done is clearly mentioned. This is example. If there are 1000 frames in a video, then a certain portion of 50% of the initial 500 frames is segregated as a training, and remaining 500 for the testing. So whenever the scene dependent, the things are very clear. So you don't need to be worried which frame to keep, which frame to skip, whether I need to go for the random selection for the training and all. Nothing like that. Just simply n number of frames divided by 2, divided for the training and testing. That is called scene dependent evaluation. So as I said, even in the scene dependent evaluation, we have categories, and we have complete. So this is also done algorithm tested on category wise as well as the complete data also. So as such, we have 4 different set of data division strategies are there. Apart from this particular thing, these are few implementations. You can go through it. Yeah. Apart from this particular scene dependent, scene independent, category wise and complete, there are few more things also we can observe here. In the scene dependent evaluation, if you'll observe the results from this particular table, initially there is no such training data that is called 000. As I said that in the traditional approaches, we are not followed any other training, only the testing data. Every data is entire data is a test data only. But as comes to the deep learning, there is an issue of training and testing. If you try to observe these particular things which are highlighted here, 50%, 100%, and so on. So the algorithms are trained on 50% of the data, but they have tested their data on the 100%. That means you can train your data on the 50%, but you try to test on the entire data itself again. Yes, please. Any questions?
No, sir, you can continue. Probably it was by mistake.
Okay, fine. So what is meant by training on 50% and testing on 100%? The logic is so simple. Let's assume you have 1,000 frames. Okay, they might be initially trained their model on the initial 50%, for example. But the testing results, what mentioned in the article, are a bit different. Because initially 50% you have used for the training, but during the testing, you're trying to test on all the frames. That means the frames which are used in the training also you have reconsidered for the testing. Let's assume in the training accuracy, you might be got 80%. So definitely the testing accuracy will be 80 plus will be the testing accuracy, because the trained data again you're using for the testing. So definitely there will be a boost in the overall results. So that is what the actual observation in the literature, that by using deep learning, it is not necessarily to only focusing on a overall accuracy. It is also an important factor that how this particular accuracy is calculated. So in order to prove that, so in this article also the authors have followed the similar strategy, initially 50% and 100% of testing, and initial 50% and exact 50% by the testing and training. The things have done in both, one is category wise, also in the complete data set. And here you can able to see the results. So this is a scene independent evaluation. Now also if you'll observe scene independent evaluation, in the previous case is a scene dependent. So in the other case is scene independent. So in the scene independent, so there is no dependency, there is no concept of 50% training and 100% testing, because it's completely scene independent by using the leave video one out strategy. So if you'll observe the results here, category wise and complete, you can able to see results. Yeah, you can observe few of the articles here. They have also followed the scene independent evaluation, because they followed our article. They followed one article which is published in the some IEEE signal processing letters, and they followed that particular strategy and propose some approaches. And the similar strategies applied in various data sets by addressing various challenges. And in this article, you can also able to see there is a much ablation studies also given. So within the ablation study, what is importance of the MSR block batch, what are the multiscale multi-maximum receptive fields which they have introduced, you can remove that and you directly can pass the current frames, because the MMSR will going to play a significant role, but still you can remove it and you can pass it to the network. And temporal median also you can remove, and so on. So there are the modules which are introduced in this particular framework. You can remove those modules and you can test. So like that the ablation studies have done, and these are the few results. And this is the speed of the particular thing and the parameters of the model. Parameters of this particular network is very, very smaller as compared to the existing architectures. This is the actual major overall observation of this particular deep learning models in the change detection is the articles are giving the better accuracies if you'll follow the scene dependent evaluation, but the same algorithm will going to degrade their performance whenever you follow the scene independent evaluation strategy. Because as that is what the theoretical observation is hence proved with the practical experimental results. So whenever you're trying to do the scene dependent evaluation, you will definitely will going to get the better accuracies as compared to the scene independent evaluation. Because in the scene independent evaluation, you need to develop an algorithm in such a way that it has to handle many of the problems, many problems. So this is one article. These are the few results. Later on, from the similar group, there is another article that is published in Transaction Image Processing 3D-CD. So this is the architecture of 3D-CD. Yeah, one another important thing which forgot. These particular algorithms can be used for real-time validation. So if you will see some of the articles as in the previous article we have mentioned, those articles which compared are not for the real-time validation, because there the chunk of 50 you need to wait to get the 50 frames at least. But the article which we have recently discussed, just before we discussed our current article, what you are able to see it here, these are all the for the real-time validation. It's nothing but in real time, for each and every frame you can take a decision. Initially you need to estimate the background. For the initial 50 frames or 30 frames you will not get the result, but from the, let's say, assume initial k frames you consider for the background, then from k plus 1th frame to the nth frame you can able to calculate the result. So these are the models for the real-time validation. So this is one another model in TIP, another architecture in TIP. So we have a number of frames. First you need to estimate the GRB, that is called gradual reductionistic background estimator. Then they have passed this information to FSR, that is called foreground saliency representation. Then some multi-schematic encoders and multi-schematic decoder they have introduced. Let's try to observe one other things. As I said, that GRBE, the aim of the GRBE is to you need to reduce the temporal depth gradually so that you can able to come to a conclusion of a single background frame. So initially they have used 50 frames, then they have used a temporal stride of 5 so that they come to 10 frames, then temporal stride of 2 they come to 5 frames, then temporal stride of 5 they come to single frame. So gradually they have reduced the temporal sequences to 1 so that the background frame can be observed. Then the important thing is motion saliency, because we need to estimate the motion, so that they have used the CMF block, that is called coarse motion features. So in the coarse motion feature, they have used this differential layer, that is called, what are the model you have estimated, that is called background, and the current frame, that is called K plus 1th frame. You try to take the difference between these two so that you can able to get the motion features. If there is a change in the current frame, you will get the motion features, and those features you can simply pass to the encoder decoder. But there was a small observation is that whenever you are trying to take the difference between the current frame and the estimated background, simply difference, there may be some unwanted information may also going to appear, maybe because of the noise, maybe because of anything, or we won't get the fine-tuned information. But in order to get the fine-tuned information, fine-tuned motion information, the CMF features can be further fed to single convolution operation, so that the convolution operation may go into remove information, or it can able to get the fine-grained information. That was the actual intuition. So by passing this particular CMF to one convolution operation, we can able to get some fine-grained features, and the features from the current frame, and again from the features, what are the coarse motion features, both you can concatenate, that is called FSR, that is called foreground saliency representation, and you pass it to encoder decoder concept. Now if you'll observe in the encoder decoder, if you'll try to see the diagram here, generally in the literature you can able to see multi-scale or multi-level encoders with a single decoder, but in this article you can able to see the multi-level encoder with the multi-level decoders. So in between the encoder features, they have used the residual connections here so that the fine-grained information and the previous actual foreground information can also be preserved, because our target here is to estimate the foreground information. And also, if you observe this particular decoder here, multi-level decoder have used, and at the end there is a CFD. So is the CFD is a convolution operation, force foreground detection. So the purpose of the CFD is to fine tuning this particular decoder responses, because here multi-scale features they have used, multi-level features, and these all multi-level features are concatenated and compared with the ground truth. Before comparing the ground truth, here the multi-scale features are there, so multi-level features are there. In order to compare the multi-level features, you can fine tune further, then you can able to compare, so that model can able to betterly train. That was the actual intuition of this entire approach. This is a pictorial representation, as I said, from a temporal sequence initially estimated background. You can able to observe here the background information. Let me show you. Yeah, this is the background information here. From a current frame, you can able to get the from the current frame and an estimated background. You can take the difference between these two. You can able to get the CMF features. That is called coarse motion features. See if you try to observe the diagram how fine it is, because we are going to we are passing this information to the convolution layer and we are fine tuning the things. Then you are passing to this entire thing to FSR, foreground saliency representation. Once you got the foreground saliency representation, you try to observe here, then this particular information you are passing to CFD for the foreground detection. And this is the post processing, so that you can able to finally get the, if any of these small holes will be there, and all the holes will be going to be removed or holes will be going to be added. So the 3D and the strategies by addressing the challenges in the literature. And this particular problem also again tested on the scene independent evaluation on multiple category wise and complete and so on. Much complex experimentation here you can able to see in this particular algorithm. And of course, applications also done. You can, if anybody interested, you can see it. Yeah, you try to observe this. This is an algorithm for results. If you have any questions, please discuss with me. Any questions? Participants, do you have any questions as such? Okay, fine. Now let's move to the next problem, that moving object recognition. So if you'll see in the literature, as I said, stated earlier, in the literature, we might be seen about the concepts called object detection, or we might be seeing a concepts of moving object detection. But there is a new strategy which is introduced that is called MOR, moving object recognition. So moving object recognition is nothing but, this particular strategy is a first algorithm in the application which is going to simultaneously localizing and as well as a classification problem. So you are trying to detecting the moving objects with the help of simultaneous localization classification, which is the which is followed in the object detection concepts. What is the technical difference between these three? Let's have a look into it. Let's assume this is a video frame sequence here. So if you will go to do the basic concepts of object detection, if you simply follow the object detection, you try to observe here how many number of objects you can able to see it here. Let me zoom it out. Yeah, whenever you're trying to take this frame sequence, or let's assume this is the frame which is highlighted on the bounding box here, you can analyze this. If you are going to use the same frame for the object detection, you are passing to the object detection. Here you can able to get the n number of objects, the objects which are in the parking lot and the people who are trying to walk the right? But the traditional way of solving the problem of object detection is like this: pixel-wise binary segmentation. So if you'll observe here, the cars which are detected in the object detection is not detected in the second frame. But here the output is something in terms of binary response. But there is a strategy which this algorithm has introduced, that the way the moving object detection is happening in the conventional way, only the foreground information is going to be detected, but this time is with the help of the bounding boxes. So you may think that, so you can able to observe, this is another example. This is a data which sample which I tested in my previous organization. It's MNIT. So in the object detection, see how many number of objects have detected from the moving object. This is the actual motion, and this is the actual motion is going to detect the bounding boxes. So the question comes here is, why should we do or follow or adopt this particular strategy? What is the advantage of doing this? The first advantage of doing this is, whenever you want to do the moving object detection at your own premises, if you want to develop an algorithm, or you want to customize an algorithm as per your requirements or as per your environment. Now, first question will come here is, how you can able to train your model, from where you will going to get the ground truth. You need some ground truth information, right? If you want to customize the things as per your institute, then you need a ground truth. You need to record a ground truth. How you can able to generate this type of pixel-wise binary segmentation ground truths is the first question. Because generating such type of ground truths itself is one of the biggest challenging problem. But as such, generating this particular bounding box ground truths are much easier as compared to generating this particular pixel-wise binary segmentation. Because in this case, each and every pixel we need to analyze, whether it is a foreground or background and so on. Even in the foreground, depending upon the size of the object, the entire size of the object needs to be detected pixel-wise, and we need to calculate. So that is a bit tedious task as compared to the bounding box strategies generally we used to follow in the object detection. So in this article, they have integrated two different solutions together to solve a completely new problem, that is called, with the help of this bounding box strategy generally followed in the object detection, and also the background estimation concepts from the moving object detection. By integrating these two, they have introduced a concept called MOR, moving object recognition. Now, as I said, as it is the first article in the literature, you don't have the labeled information or ground truths. So these authors have proposed these particular bounding boxes, or these labels are created in a popular data set called 2014, because as it is the initial attempt of doing it, so there should be a benchmarking data set is required to generate a benchmark results. So they have tested their model on the same CDNet 2000 data set by creating their labels of around 24,000, it's around 42,000 objects they have annotated with the two classes. One is a cars, another one is a persons, and so on. Then they divided the data for the training and testing. So this is about the data set details. These are a number of videos I have used for creating the labels, and this is the training data, and this is the testing data. The data set is introduced. Now we need to test the model. So in order to test the model, they have adopted the concept of RetinaNet. So RetinaNet is one of the popular technique in the object detection concepts, because we also want to do the objects, but we are trying to do the moving objects. So in the object detection concept, if you try to observe here we have integrated two different concepts of change detection as well as the object detection. So object detection concept RetinaNet they have used for the framework, but initially the n number of frames, as I said, 50 number of frames they have initially used, that is called recent history frames. From there, the step is to estimate the background. First they estimated the background, and they pass a temporal median as a supporting frame, then current frame to calculate the saliency motion estimation. So they integrated all the three together and pass it to the backbone model. So in the RetinaNet, the background model they have used is the ResNet 50. Now, if you observe in this particular diagram, they parallelly have passed the current frame to ResNet 50 separately also. It is not necessary to feed it, but in this article, they have feeded the integrated features here to the backbone model that is called ResNet 50, and the ResNet 50 features we got it that is called backbone features. So the backbone features which are extracted from the combination of estimated background and temporal median current frame, you got backbone features that is highlighted in the brown color, orange color, and the backbone features which are generated from only current frames also going to be extracted and combined together, that is called assimilated features. Now these assimilated features are now passed to the next level model that is called multi-level feature pyramidal structure used in the RetinaNet. So the aim of this using this multi-level feature pyramidal structure is to handle the multiple object sizes. So multi-level, each level is going to taking care about the different scale of the object. So there are 5 level multiple pyramid structures are there, and for each structure they have calculated 2 different losses together. One is called a regression loss, another one is called classification loss. So that is how it is a simultaneous localization and a classification problem. So this is called TDR block, that is called temporal depth reductionistic block from k number of frames. So here the temporal sequence is 10, 20, 30. Some of the ablations are already available. So from k number of frames, we need to first estimate the background by gradually trying to reducing the depth of the frames from k to 1 with the help of this multi-scale features. So this is called the background estimation, that is called TDR response. So you can able to see only the background information is going to be estimated here. Then we have passed the multi-level feature pyramid. So from each pyramid, each level, we can able to extract the features. These are all the features you can able to see it here. This is called heat map representation. From a given sequence, first level pyramid, second, third, and fourth. Fifth, we have not able to show here is because size of the object is very smaller and size is difficult to view. So if you will observe here, if whenever you are going to use a bigger size frame, you will have the bigger size, and we are gradually trying to reduce it. The size of the bounding box is also going to be reduced depending upon the object size. So still we need to recognize that is how we are trying to follow this particular multi-level feature pyramid structure. Now you see this, as I said, this is a benchmark result. So instead of using they have tested their model with the ResNet 50. In place of ResNet 50 backbone model, you can also use the compact model that is called MobileNet also. Or if you want to use any other model, that's all up to you. What are the model you want to use it as a benchmark model? Yes, you can able to use it for the backbone model. Now initially, if you'll see, the input given features are depth of 10, 20, and 30. So by changing the depth also will going to play a role. And they have also tested the model with the 2 different versions. One is mobile rec 1 and rec 2. One is nothing but by assimilating the features of estimated background, temporal median, and current frame, and also the current frame backbone features. So combining multiple backbone features together is the version 1. Only passing assimilated features of temporal median, current frame, and estimated background is one thing. By removing the current frame also they have tested. So these are the 2 results. As you can able to see it here, by removing the current, if you don't want to pass it current frame to backbone model, that means 50% of the parameters have drastically has reduced. Now you try to observe here. If you are trying to assimilating the things, you are going to get 263 MB, but you are trying to simply removing current frame, then you are going to end up with less, half of the parameter size. Here you can also observe here almost 36 million and 65 million. So these are all the results of intersection over union. And whenever you're trying to use the intersection over union of 20%, you will going to get the better results. Whenever you're going for the 80% of the intersection union, the results are going to drastically reduce. So this is that various positions you are going to get the results, IOU results. Now you try to observe here. In this example, see the vehicle was moving here, and the moving vehicle is detected with the bounding box. But if you try to observe in this example, in the background there is a snow and there is a flag is moving. So as you knew that Here the flag movement is actually because of the wind. So it is a natural problem. It is not actual true motion, right? So those things we should not recognize. Here we should only focusing on the moving objects. Now if you'll observe here, whenever the object is going to be stopped in the parking lot, the bounding box is going to be ignored. Now you try to observe this example here. The only one person is trying to walk here, and the rest here in other things like cars and vehicle, many things are there parked in the parking lot, and these all the things are not going to be recognized. But that is what our target is. We should not recognize all the objects. We need to recognize only the moving objects, that too with the help of the bounding boxes. So whenever you're trying to use the bounding box concept for the change reduction, these particular shadow problems and all will going to be ignored. You can easily able to handle that particular issues of shadow and so on. Right? This is the thing. Now coming to the same problem of change reduction from an aerial view. If you want to do the similar problem from the aerial view instead of going for the conventional view, yes, we can solve the problem from the aerial view. So yeah, these are all the challenges which generally we are going to face from the aerial view. Let's assume the problem which we have solved in just before is a change detection with the help of bounding boxes in a conventional view, right? Now you see this is a frame, single frame. What are the difference between the left frame and the regular right side frame? That means the frame which is captured from the regular view versus the aerial view image. If you'll observe these two, there is a lot of proper changes are there. One is number of objects which are there in a single frame, that is called in a regular view. Here only finite number 2, for example. But here you will have many number of objects. Second one is size of the object. Here the size of the object is very bigger in size. One particular vehicle is trying to occupying more space in a given frame. But here in the right side, if you'll observe, the size of the object is very, very smaller in size. But technically, if you'll observe, this is also a car, and the right side is also having a car, and left side is also having a car. And the third observation here, if you'll observe here, that background information. Here in the regular view, you can able to get the normal background, not that much challenging. But in the right side, if you'll observe, there is a lot many challenges are there in the background. So the algorithm which you might be adopted in the previous case may not going to help you here in the right side, because here, even though aim is to detect the moving object from the aerial view, that is also MOR, but these are all the challenges will going to play a very important role in the selection of the algorithm or selection of the frame. Let's take an example of how to solve it. So as I said that as this particular approach was not there in the literature, so we created own data sets to solve this particular problem. First one is the ABD dataset, airborne dataset, where we have annotated almost 42,000 objects are annotated. It is divided into training data and testing data by injecting some challenging of non-uniform class sizes. So this is the things like if you have a different set of data sets, car, heavy vehicles, planes, boats, and all. If you'll observe this, where we have n number of car objects, and as we have a limited number of plane objects, then how you can able to solve it? This is one challenge which you have addressed in this particular data set. So this is one of the data set. If anybody interested, you can just freely can access this by filling one particular form. From an aerial view, also the data set has created. Now you try to observe this. This is the data set of the aerial view. This is a framework. So if you'll observe the framework here from a sequence of frames, the simple background estimation will not going to help you. So you will need some different strategies so that we can able to estimate the motion is our target. So here the thing is that instead of simply estimating a background, here we trying to calculate the motion with the help of the optical flow. So initially we have estimated with taking the optical flow with different size of frame size, with a single frame, with 3 frames and 5 frames and so on. That is a temporal sequence of 3 frames, 5 frames and so on. To calculate the optical flow, then those pieces of optical flow features and current frame is passed to the retinet as we have discussed earlier. So if you try to focus on estimating a background here from the area, for the aerial view, it will be very difficult for your model to converge because the background is very challenging here. It will be not that much easy to detect the background and estimating a motion. So instead of that, simply you can, in this example, we have used the optical flow concept to get the results. So this is a pictorial representation. If you try to observe here you can able to see up to 3 levels only, even though you have used the 5 levels. You try to observe here, the size of the object is very smaller in size, very smaller in size. See the heat map representation wherever the motion changes are happening, because that we are trying to estimating the change, electrical motion, with the help of optical flow. You can able to see the change information is clearly highlighted here. So the things have done up to 3 level, but in the 4th level it is very difficult to visualize. So yeah, here in this article others have shown up to 3 level. So this is about the data set. Almost 52,000 ops have annotated. In this case, they try to balancing the number of different objects. So here the total number of objects, if you will observe here, cars and heavy vehicles are 2 different objects. So as is the first article in the literature, so this is the different results of baseline results you can consider. This is IOU. Yeah. If you have anybody having any questions, please raise your questions. We can have a discussion.
Any questions from the
If
participants?
anybody having, yeah, if anybody having any questions on that, please you can discuss. These all the data sets and codes and all whatever you have discussed right now. You can easily it will easily get it from the website which I have mentioned there.
Sorry.
One
for your
question
easy
from my
reference.
side, Santosh sir.
Yes, ma'am, please.
Like in SDE, you said na ki we take 50% for training and 50% for testing. But generally we go for 80-20 rule or 70-30 rule. So why there is a difference in that?
The entire idea of using this particular thing was we should not follow this scene dependent evaluation. We should not follow.
Acha.
If we will go for the independent, that is the best way of solving the problem. We should not go for the dependency. Now, if you'll go for the 70% and if you'll go for the 80%, but still the background scenarios remain same.
Okay. So just
that
to reduce the dependency on the training set, you are reducing the size of the training set, is it?
No. We are not reducing the training set. We are trying to addressing the problem of we should not follow any data division. Even though you go for 80-30, you go for 70, 80-20, 70-30 or 50-50, whatever the thing you will going to follow, you can follow it, no issue at all. But the question here is training data and testing data should not have the similar information. That care we should take care.
That is fine. Training and testing should be different. Sure.
That is
Yes.
So in this case 50-50 we are going to use, because in the literature most of the articles they have followed 50% for the training and 100% of the testing. So
They have used the training data also for the testing.
Yes, exactly. That is a wrong thing, right?
Oh, okay.
Because these particular problems have arisen because of only one reason, that is that most of the reviewers were only focusing on the accuracy in the name of deep learning. So in order to get the accuracy, they have shown their accuracy in this way.
Okay. Makes sense. Yes. Thank you for the answer.
Yeah.
Any further questions from anyone?
So if anybody having any questions, discuss with me. And for more details, I already shared this website. From there, if you want, you can explore the things. Okay, as such, I think there are no more questions. So.
Okay, sir. Okay.
Okay. Once again, thank you.
Okay, thank you so much. Thank you so much, Santosh sir, for accepting the invitation and giving this wonderful talk. It was really very helpful. And you talked about all the implementation details also. Thank you so much, sir.
Okay. Thank you, ma'am. Thank you, Dr.
Thank you.
Pooja.
Thanks a lot. Hope
Okay.
for further future collaborations.
Yeah, sure. Thank you.
Okay. Bye-bye. Thank you.
Bye. Okay.
Thank you all the participants. That was the end of the session for today. We'll meet tomorrow at 9:30.